Dear friends, welcome back. Let's now proceed to analyze the stability of a wing and tail combination, where in our previous lecture we talked about wing alone configuration, for which the Cm about Cg we have estimated, and then we bifurcated that into two components, Cm naught and Cm alpha, where we figured out Cm naught has to be, for Cm naught has to be greater than 0, right? We need to have a reflex aerofoil for a wing alone configuration, and then for Cm alpha to be less than 0 for static stability condition. To satisfy that condition, we need Cg should be ahead of the aerodynamic center. Okay. Now let's look at the contribution of wing and tail combination and its contribution towards static stability. So I'd like to divide this into two partitions. So now let's have this wing and tail. So say this is my fuselage reference line. Say our wing coincides with the chord of the wing coincides with the fuselage reference line here. Say this is the chord. Okay. So the chord of the wing coincides with the fuselage reference line, and then we have a tail at aft the wing, right? And then we and also let's not consider about the z offset of the CG. Okay. So we have fuselage reference line, and for the wing we know there is an aerodynamic center for this wing, which is located at a distance x AC aft the leading edge of the wing, and the CG of this aircraft with a tail, we'll draw the tail very soon. So is located at a distance x Cg with respect to leading edge of the wing. Okay. And we have a tail here. We added a tail. Let's say the chord line of the tail is oriented or inclined at certain angle called I of t, right? Tail setting angle. I of t is known as tail setting angle with respect to the fuselage reference line. So this is a chord line of the tail, horizontal tail, and I of t is the inclination of this chord line with respect to the fuselage reference line, and we call this I of t as tail setting angle. This is tail setting angle. And in general, this tail is a symmetric, the cross section of tail is a symmetric aerofoil. Why? Because we know it has to produce equal amount of force on the either side of the deflection. The aim of the tail is not to generate lift, to generate a moment, right? To control the orientation of the aircraft, and also to provide static stability. So that we'll see how to control the aircraft, that we'll see later when we talk about elevated deflection. So for the time being, we assume the tail is used to stabilize the aircraft, and we'll see how it is going to do that. And the tail is also located at a distance, right? We also have an aerodynamic center for this tail, which is located aft the leading edge here, and is and the corresponding distance here is x AC of tail with respect to leading edge of the root chord of the wing, and is measured parallel to the fuselage reference line. So this is my fuselage reference line FRL. Now when this is moving or in equilibrium at certain alpha, so moving at certain V infinity, this combination is moving at V infinity. So we have lift perpendicular to V infinity, okay, lift of wing, and at the same time we have moment about aerodynamic center of wing, right? Similarly, we should have lift at the tail as well, right? So, but the flow near the wing may not be same as flow near the tail. Why? Because the wing, we witnessed, right, from the lifting line theory, it creates a downwash behind the wing, isn't it? So because of the downwash, say this is my, so V infinity, actual V infinity, right? So ideally, this has to be my angle of attack. Ideally, it has to be there. But because of the downwash, no, there is a downward component of velocity. Downwash is nothing but the flow is pushed down, right? It was pushed down by this wing, right? It is heavy near the wing, right? In the vicinity of the wing. As we go behind, because there is a forward component, right, of the velocity. There is a like component of velocity in this direction, and there is a downward direction, and the component of velocity which is in the direction of flight or in the direction, so is higher, right? Which means the free stream velocity is in the opposite direction to flight. So which is higher, so the resultant will remain flat, but still there is some deviation from the actual flow that the wing faces. Right? So deviation at the tail compared to that of what the wing faces. So that is nothing but the downwash because of this, induced because of by this wing, right, at the tail. Right, say this is the downwash, so because of which the resultant free stream velocity here will be flattened. No? This is my velocity at the tail, Vt or V prime we call it. Let's say V prime here. Okay. So V infinity prime. Okay. So this particular change in angle is epsilon. Okay. Is it clear? So now effectively I can, so this is equivalent to this. So say, so this is equivalent to, these two are parallel, right? So this is my V infinity and this is my epsilon. So now the angle of attack that this tail C is with respect to this V infinity prime, right? Isn't it? So V infinity prime is the modified velocity at the tail because of the downwash induced by the wing, right? So this downwash creates an angle epsilon with respect to the free stream velocity at the wing, V infinity. So now the angle of attack that the tail C is with respect to this modified velocity which is V infinity prime, and it is denoted by alpha at the tail, right? So this alpha at the tail, I can express this in terms of known quantities. For example, so I know what is tail setting angle here. I know what is wing angle of attack, which I will be measuring using an angle of attack sensor there, right? So I know alpha, I know wing setting angle. So can I express this in terms of these parameters? And I can model this downwash. You know, it is similar to that of alpha I, right? Do you remember? So this epsilon can be modeled. So is twice that of alpha I at the downstream. So this is from the lifting line theory. This is 2 times of CL upon CL of wing, right? Because this epsilon is because of the wing here. So 2 pi E AR, right? So this is how we generally estimate this. This can be expressed as a function of angle of attack. So dou epsilon by dou alpha times alpha is equals to 2 times CL naught of wing plus CL alpha of wing times alpha upon pi E AR. So from this we can say that epsilon naught is equals to 2 times CL naught of wing upon pi E AR, and epsilon or dou epsilon by dou alpha is equals to 2 CL alpha of wing upon pi E AR, where E is the Ostwald's efficiency factor, AR is the aspect ratio. Fine. Okay. So once we know epsilon here, we will be able to, epsilon is also known. Once we know CL alpha and the wing geometry, we will be able to find out the induced downwash because of the wing at the tail, right? So now we know, if we know all these quantities, like say I of t, alpha and epsilon, now I would like to express this tail angle of attack in terms of these known variables. So alpha t is equals to alpha, right? So this is alpha minus this particular angle will fetch me this particular V infinity angle made by V infinity with respect to fuselage reference line, right? That angle plus I of t will be my total angle of attack. Okay, so alpha minus epsilon. So epsilon is because of the downwash here, right? So indicated by this green line. Alpha minus epsilon plus I of t is the tail setting. Okay, so what I can do further? So alpha of t is equals to 1 minus dou epsilon by dou alpha times alpha plus epsilon naught plus I of t. Isn't it? Am I correct or not? So if I substitute this particular expression in that equation, what is alpha t is equals to what epsilon can be minus, okay, so this must be I of t minus epsilon naught. So this is I of t minus epsilon. So that epsilon is equals to minus epsilon naught minus dou epsilon by dou alpha times alpha. So if I substitute that and take alpha common out, so separating the coefficients of alpha and constants, I'll have this particular expression. Okay. So with this derivation, we now can proceed with this understanding. We now can proceed with the modeling of moment for this particular configuration, wing and tail configuration, and we'll find out what is Cm naught and Cm alpha for this configuration, right? At the same time, we'll also look at what is the total lift from this wing, from this combination, and then also the Cl naught and Cl alpha of this configuration, wing and tail combination. So now we know so the lift at the tail will be acting perpendicular to V infinity prime, which is L of t, right? There will be a little drag, but we are neglecting the drag. That horizontal component or the vertical offset of CG is not considered, right? And we proved that that is not affecting much. With that flat plate flight, we demonstrated that if that is small, it is insignificant for static stability contribution, isn't it? So I have L of t, but I don't have a moment here, isn't it? Do I have a pitching moment coefficient about or moment about aerodynamic center? Why? Because we are using a symmetric tail, right? In general, it is symmetric tail, right? So made out of symmetric aerofoil. So we don't have CMAC there. So now the wing lift, so and assuming a small angle of attack, so LW cos alpha will be LW lift off wing multiplied by this offset with respect to CG contributes towards pitch up moment, right? So now taking moments about CG and lift off tail contributes towards pitch down moment. Am I correct or not? Lift off tail multiplied by the offset between this. Offset is what? This particular distance, which is like the total distance of tail with respect to leading edge of root chord subtracted by the distance of CG or the distance of CG with respect to leading edge of the root chord. If I subtract this distance from this total distance, what I have is this particular distance, the momentum between CG and the aerodynamic center of tail. Okay. So now, what is the total lift of the aircraft? A by C stands for aircraft here, or say this is nothing but total lift of the aircraft. L is equals to lift of wing plus lift of tail from the principle. So do you remember those assumptions? Like one of the assumptions talks about principle of superposition. Right? So the total lift here from that assumption, it is equals to lift of wing plus lift of tail. So this is equals to, so half rho v square. So aircraft free stream velocity is equals to the wing free stream velocity times the reference area of the wing is reference area of the aircraft. CL is the CL of the aircraft is equals to half rho v square S times CL of wing plus half rho v prime square, isn't it? So V infinity prime square, or say V infinity prime square, which is at the tail. This is the velocity at the tail, times S of the tail, right? So the lift generated by the tail is due to the area of the tail, isn't it? Planform area of the tail and the velocity at the tail. The velocity at the tail, we figured out it as V infinity prime, which is modified due to the downwash. And then the reference area of this tail is nothing but planform area of the tail, which is S of t, right? Times the CL of tail here. Okay. So now if I simplify this further, so the CL of the total aircraft is CL of wing plus half rho V infinity prime square upon half rho V infinity square, right, times S of t upon S times CL of tail. Okay. So this particular factor, velocity at the tail upon velocity of like dynamic pressure at the tail upon dynamic pressure at the wing, this particular factor is known as tail efficiency factor. Okay. So this can be further written as CL of wing plus tail efficiency factor, which is eta of HT times ST upon S times CL of tail. Okay. This is one important expression. Fine. So further, if I want to know what is the CL naught of the total configuration and CL alpha of the total configuration, what I can do is I can express in the linear regime of angle of attack the total aerodynamic CL is equals to, as a function of alpha, which is CL naught plus CL alpha of the total aircraft times alpha of the total aircraft, which is equals to CL naught of the wing plus CL alpha of the wing times alpha of the wing, isn't it? From the linear approximation, from the plus eta of tail times S of t upon S times CL alpha of tail times alpha at tail, right? This CL at tail is varied because of alpha at tail, isn't it? And we know that since it's a symmetric airfoil, symmetric tail, we have CL naught 0 of the tail. CL naught of the tail is 0. Okay. Okay. So this is alpha and V infinity, right? This is our FRL. Tricky. So by comparing, so what is alpha of t? So this is CL naught plus CL alpha into alpha of the entire aircraft is equals to CL naught of wing plus CL alpha of wing multiplied by x bar CG minus, into alpha of wing plus eta. This is nothing but alpha. Alpha of wing is nothing but alpha here, isn't it? So eta of horizontal tail times ST upon S times CL of tail multiplied by alpha of tail. What is alpha of tail? 1 minus dou epsilon by dou alpha, right? Alpha of tail into alpha plus I of t minus epsilon naught. Okay. So by comparing the constants and coefficients, the CL naught of the entire aircraft is equals to CL naught of wing plus eta HT of horizontal tail multiplied by ST upon S CL alpha of tail multiplied by IT minus epsilon naught. So you can assume epsilon naught is small, otherwise epsilon naught in general is positive. You saw that expression, right? So epsilon naught is 2 times CL naught upon 2 pi EAR. So that's a positive expression. So we can keep it as it is. So this is one equation that talks about total lift of a wing and tail combination. Okay. So and then we'll talk about CL alpha by comparing the coefficients of alpha. What I have is CL alpha of wing plus, so I have a coefficient for alpha is CL alpha of wing, and there is a coefficient for alpha from the tail contribution, which is horizontal tail times ST upon S times CL alpha of tail, CL alpha of tail times 1 minus dou epsilon upon dou alpha. Okay, this is the contribution from tail here. Okay, sorry, wing and tail combination. Okay, so we have the CL alpha of wing. So for a wing alone, these two terms disappear, isn't it? So we just had this for wing alone confidence. Total aircraft CL naught is wing CL naught, and total aircraft CL alpha is wing CL alpha. Okay. Now we need to talk about moment. Right. So this is the lift details about the CL naught and CL alpha of the entire aircraft. Now let's talk about the pitching moment, about CG. So about CG, the y-axis is into the board here, right? So y-axis is into the board. So any moment that creates pitch up, nose up moment for this UAV, nose up motion is considered as positive, and nose down, the moment that creates nose down motion is considered as negative moment, right? So now the moment about CG of this aircraft is nothing but moment m is equals to moment about aerodynamic center of wing, right, plus lift of wing, right, because lift of wing is contributing towards nose up moment, right, nose up motion. So lift of wing times the corresponding distance between the CG and the AC, right. So this is the distance. So I am subtracting XAC from XCG. What I have is the momentum between AC and CG here. So multiplied by XCG, I am subtracting XAC from XCG, XAC of wing. Okay. So this is the pitch up moment, and then because of the wing, and then the tail has a lift. It tries to, there is no pitching moment coefficient about the aerodynamic center because of the symmetric nature. So we have lift at the tail that contributes towards nose down moment. So that's a negative moment, right? So which is equivalent to minus lift at tail times x AC of tail. I am subtracting this CG distance from AC of tail, right? This is AC of tail. X AC of tail minus X CG. Okay. So this equals to half rho infinity square S C bar times Cm of the entire aircraft is equals to half rho V infinity square S times C bar Cm AC of the wing, right? This corresponds to this particular term, right? This corresponds to the moment about aerodynamic center, whereas the reference area is S and the reference characteristic length is a mean aerodynamic or C bar, and the velocity of the wing is aircraft is equivalent to the velocity at the wing itself, right? So plus half rho V square S times CL of wing multiplied by XCG minus XAC of wing minus, so the lift at the tail is because of the flow at the tail, right? The flow at the tail is half rho V prime square, half rho V infinity prime square times the S of t, right? Reference area is should be S of t multiplied by S of t multiplied by CL of tail times the momentum X AC of tail minus X CG. Okay. So if I divide this entire equation by half rho V square S C bar, so I have it in the non-dimensional form. Cm is equals to, so Cm AC of the wing plus CL of wing, which is CL naught of wing plus CL alpha of wing times alpha multiplied by x bar or x bar CG minus x bar AC of wing, right? Where x bar is x upon C bar, okay? Any x bar, x subscript something by C bar is nothing but x bar subscript. Okay. So minus, what I have is half rho V prime square, V infinity prime square upon half rho V square is S of eta of horizontal tail, we just discussed. So where here, so where eta of horizontal tail is equals to half rho V infinity prime square upon half rho V infinity square. Okay. What is CL of tail here? S of t upon S. Okay. So CL of tail is CL alpha of tail times alpha at the tail, right? Because it's a symmetric airfoil. CL naught is 0 of the tail. Right? Multiplied by the momentum x bar AC of tail minus x bar CG. So this is x bar AC of tail. So this is a momentum here, right? So where x bar is equals to x upon c bar. So you can have anything in the subscript. So yeah, either CG or AC or XAC of T or wing. Right? It's a non-dimensional length, isn't it? So I'm dividing length upon c bar, which is with a characteristic length. What I get is a non-dimensional length here. So this particular term is sometimes also called as ST upon S multiplied by this particular term is also called as tail volume ratio. So V HT is equals to ST upon S times LT upon C bar, where LT is the distance between AC of tail and CG. So what I will call it as x bar AC of tail minus x bar CG. Right? But I am not going to use it for the time being. So when we talk about the iterations, then we will try to use it. Till then, I would like to keep it as it is. Right? So I am not using this tail volume ratio, horizontal tail volume ratio. This is called tail volume ratio, which is for the horizontal tail. And we also have something called vertical tail volume ratio that we are going to soon discuss about it. Okay. So now comparing the constants and coefficients of alpha. So this Cm can be expressed as, this Cm can be of the entire aircraft in the linear regime can be expressed as Cm naught plus Cm alpha into alpha. Now from these two equations, comparing the constants and coefficients, what I have is Cm naught of the aircraft is Cm AC of the wing plus CL naught of wing times x bar CG minus x bar AC of wing, right? So this is contribute, the CG is behind AC, this is contributing for a positive Cm naught. Am I correct or not? And then this is minus eta of tail, eta of horizontal tail, ST upon S times x bar AC of tail minus x bar CG, right? So this is x bar AC of tail, x bar AC of tail minus x bar CG multiplied by CL alpha of tail, CL alpha of tail times 1 minus, so I of t minus epsilon naught. Okay. This is my expression for Cm naught. So you need to, whenever it is required, you should be able to derive it quickly. No, it happens by practice. You need to practice this multiple times, and you need to understand the contribution from each and every term so that you can easily get back to this equation. So we'll do it couple of times so that you will also be comfortable with the terms here. Right? So this is Cm naught, whereas Cm alpha of the entire aircraft is from CL alpha of wing multiplied by x bar CG minus x bar AC of wing, right? And minus of eta of tail, eta of horizontal tail, and then S of t upon S times my x bar AC of tail minus x bar CG, right, times the CL alpha of tail multiplied by 1 minus dou epsilon by dou alpha. Right. This is the Cm alpha of the entire aircraft. So for this aircraft to, so it's an important expression, so please try to derive multiple times so that you can get used to this equation. So in this equation, if you can see, what we need, our aim is Cm naught has to be less than 0 and Cm alpha has to be greater than, Cm naught has to be greater than 0 and Cm alpha has to be less than 0. So look at this particular expression. So for Cm alpha has to be less than 0, say if the CG is behind the aerodynamic center, okay, if the CG is behind the aerodynamic, this contributes towards positive pitching moment, right? So this first term contributes towards positive pitching moment because CL alpha, of course we know it's positive. So eta is positive, SC upon S is positive, and then the tail is behind the CG, right? This is positive, this contributes towards positive, and CL alpha is positive. So 1 minus dou epsilon by dou alpha is always less than 1, less than or equal to 1 at maximum, right? So yeah, second term is negative. Have it. So we need to choose this particular number strong enough to overcome this positive, right? So the offset between these two should not be very high, okay, so that the tail volume should overcome this particular positive term. So if you have to design this particular term is known as tail volume ratio, as we discussed. So you need to choose a particular tail volume ratio in order to make this stable. Because it is obvious that when you have a wing and a tail at an offset, the CG will of course be behind, right? Isn't it? You have to mount your engine and you have to place your batteries in such a way that you bring this particular CG as close to this aerodynamic center as possible. Okay. That is what. No. So now looking at the Cm naught term, the CMAC of the wing is, let us say if you use a cambered aerofoil, this is negative, right? Cambered aerofoil. So in a previous lecture when we talked about reflex aerofoil, you witnessed that the CL alpha is very less comparatively, isn't it? CL alpha of the aerofoil itself is less. Why? Because you need to compromise with the camber. Towards the trailing edge, for a reflex aerofoil, it will be upwards, right? To provide a pitch, bend upwards. So bent upwards so that it will obstruct the flow, and the flow it pushes down, it gives a couple, no, at each and every angle of attack. Due to that we are compromising with the camber, that means we are compromising with the CL alpha, which we have witnessed. But in case of cambered aerofoil, you have very high CL alpha, right, compared to the reflex aerofoils and the normal aerofoils. But you have to compromise with that negative pitching moment here, right? So you have CMAC negative here, and if this is positive, right, this contributes towards positive. And when you have this tail setting angle, say if this distance is very less comparatively, let us assume, right? So in order to overcome this moment about aerodynamic center, this is negative, right? So say if this distance is very less, then you need to have a tail setting angle here, right? So why? Because this is positive, and this is positive. We know that because aerodynamic center of tail is behind the CG, and then S of t, these two are positive quantities. CL alpha, of course we know it's positive. So I of t minus epsilon naught. Epsilon naught is positive. So if I of t is negative, this entire term will be negative times minus negative, is like it contributes towards pitch up moment. That means I of t, you need to have negative setting angle. What does it mean? So I of t is positive above, when inclined above the fuselage reference line. So I of t is positive when inclined above the fuselage reference line, right? It is negative when it is inclined or oriented below the fuselage reference line. Okay. So that means you need to set your tail with a negative orientation with respect to fuselage reference line. So by doing that, what you are exactly doing, when there is a flow, so you are obstructing the flow, there is a downward force. So this downward force, even at zero angle of attack, right, will create a pitch up moment about the CG. isn't it? So that continues, that Cm naught, the contribution of tail towards positive Cm naught continues, whatever the angle of attack it is, right? So this becomes what? Positive quantity here, right? So with a proper value of this, it becomes more positive. You can trim at higher angles of attack as well. Okay. So that means more the value of Cm naught, more the trim value that I can achieve, isn't it? So that this particular quantity alone can overcome this particular limitations. Let us say in the case where you want to have I of t 0, right? You don't want to, because you are again at the expense of drag. See, for this symmetric wing, whether is it at positive angle of attack, negative angle of attack, it produces force, same force. Am I correct or not? But in different directions. When it is in the positive angle of attack, it will produce upward force. When it is in the negative angle of attack, it produces downward force. That's why the CL variation with alpha for this symmetric aerofoil will be almost symmetric about angle of attack. Say if this is CL variation with angle of attack, right? For symmetric aerofoil, even the stall characteristics should also be same. Right? This is the CL versus, it's just a mirror image here. So if you trim it at negative angles of attack here, it will produce negative lift, negative CL, that is in the downward direction. Okay. So now when you put it at a negative I of t, it produces a downward force. At the same time, it also increases drag because of that. So in some cases where you don't want to waste additional energy to overcome the drag, what you try to do is to put to maintain I of t 0. If I do that, this particular term vanishes, right? But if I maintain some adequate distance between CG and aerodynamic center, so I have CL naught for a cambered wing positive, right? So what I can achieve is a positive value. If this is good enough, if the distance is good enough, you can overcome the CMAC negative value. So you will be still able to trim at positive angles of attack without I of t, right? For a cambered aerofoil. If you take a symmetric aerofoil, Cm naught is 0 altogether. If your wing is symmetric, Cm naught is 0. In that case, what you need to do? You need to give I of t for the tail. Always. Am I correct or not? If you give I of t, you get positive Cm naught. I of t negative for a symmetric aerofoil. Am I clear? Because for symmetric aerofoil, both these terms are 0. For the wing, I am talking about the wing. If it is a cambered wing, right? So irrespective of that, whether symmetric or cambered aerofoil, so this still remains negative. Am I correct or not? Because see, CL alpha, whether symmetric or cambered, it doesn't matter. It has its own CL alpha, right? And all these terms are positive, right? So this becomes negative, even though this CG is behind the AC, right? So this term may be positive, but still, if you choose a proper value of tail volume ratio, you will be able to achieve the Cm alpha negative. Okay, whether it's cambered or symmetric wing, it doesn't matter. But here for a cambered wing, you need to choose I of t negative, isn't it? Why? Because, or you need to choose this distance in such a way that this particular value becomes positive, right? So either you choose I of t negative, that makes Cm naught positive, because this is negative, strong negative for cambered aerofoils. Right? Okay. So that's a conclusion from here. So this, for a wing and tail combination, this is what it has to be. The Cm alpha, you get it from the wing combination as well as tail combination, right? Wing and tail combination. Now, let's find out a location. So you said this Cm alpha, you see, is about CG, isn't it? Is it not about CG? Cm alpha is about CG, isn't it? Now vary the location of CG in such a way that the Cm alpha, so we find out a location of the CG for which the Cm alpha is 0, right? We will try to find out that location, right? So that particular location about which the entire aircraft pitching moment is independent of angle of attack is called neutral point, right? Let us consider a location, some location. It is also a location of CG, right? Say this is NP, call it as NP. So this is a location of CG about which the pitching moment is independent of angle of attack of the entire aircraft. What does it mean? So Cm alpha is 0. You have Cm naught, but there is no Cm alpha about that particular CG location. Okay. So let's figure out what is that. Okay. So I'm erasing this particular part, right? And see if you can notice this particular portion CL naught plus CL, this CL naught of the entire aircraft for this wing and tail combination. Your CL naught of being positive if it is a cambered airfoil. If it is symmetric airfoil, this is 0, right? And then if there is no I of t, this term most likely vanishes without any epsilon naught, assuming epsilon naught is very small. So this term vanishes, the CL of the entire aircraft is 0 in that case, right? If it is a cambered airfoil, that CL naught is positive, right? And if you have I of t negative, this term contributes negative because you want I of t to be negative for Cm naught to be positive. Am I correct or not? So if that is the case, the overall lift of the aircraft decreases. Why? Because here near the tail you are producing a downward force, right? Near the wing you are producing a upward force. So there is a resultant force which is less than that of wing, upward, only upward force, right? Am I correct? So again you have to compromise at CL naught. If you give a negative tail setting angle, you should also compromise at CL naught here. Tail setting angle is not going to influence this CL alpha, lift curve slope of this wing and tail or the total aircraft here. Okay. So let's figure out what is the corresponding location of CG for which Cm alpha is 0. So this is that particular point is called neutral point denoted by XNP. So this particular, if I substitute 0 in the, for C, if I equate this equation to 0, right, then Cm alpha is 0, which means, so at that particular, the CG location about which Cm alpha is 0 is called neutral point. So in that case XCG becomes XNP. Okay. So what I have is 0 is equals to CL alpha of wing times x bar NP minus x bar AC of wing, right, minus eta of tail, horizontal tail, ST upon S times x bar AC of tail minus x bar NP neutral point, right, multiplied by CL alpha of tail minus multiplied by 1 minus dou epsilon upon dou alpha. Okay. So can I find out that particular NP? Can I solve it for x bar NP from this equation? So x bar NP multiplied by, this is CL alpha of wing. Okay. So I'm trying to, okay, CL alpha of wing plus eta HT of horizontal tail times ST upon S, CL alpha of tail multiplied by 1 minus dou epsilon by dou alpha. This is equals to CL alpha of wing times x bar AC of wing plus eta ST upon S times CL alpha of tail multiplied by 1 minus dou epsilon by dou alpha times x bar AC of tail, right? Okay. So this implies x bar NP neutral point is equals to CL alpha of wing times x bar AC of wing plus eta of horizontal tail ST upon S, CL alpha of tail, or say, yeah, CL alpha tail minus multiplied 1 minus dou epsilon by dou alpha times x bar AC of tail upon CL alpha of wing plus eta of horizontal tail times ST upon S times CL alpha of tail multiplied by 1 minus dou epsilon by dou alpha. Right? This is a corresponding location of neutral point. For which Cm alpha is 0. If you go beyond this neutral point location, if you locate the CG of the configuration behind the neutral point, what happens is this will become positive. Okay. So this becomes positive, which means the system becomes unstable. So do you want me to prove that? Okay, I can prove that. I can prove that. So you have neutral point here. Now, so this Cm alpha is equals to, so take out the Cg terms here, x bar Cg, right, x bar Cg times Cl alpha of wing, okay. So this is minus into minus, it becomes plus, plus eta of horizontal tail St upon S multiplied by Cl alpha of tail, okay, and then the correction factor 1 minus dou epsilon by dou alpha, right. So I am just separating Cg terms and the coefficients here. So this will be like, okay, so I have this Cg multiplied by Cl alpha is here, and then this Cg multiplied by this entire term, minus of minus, it becomes plus. I have eta St upon S, Cl alpha 1 minus dou epsilon multiplied by Cg is here, and then I have taken Cg outside, xCg, okay. So and then what I have is minus of Cl alpha, and then this minus term, so I am taking minus out here. So this minus Cl minus of, so this is Cl alpha of wing times x bar AC of wing plus eta St upon S, eta of horizontal tail times Cl alpha of tail times 1 minus dou epsilon by dou alpha times x bar AC of tail, okay. This is a, so coefficient constant terms with respect to xCg, okay. So just multiplied this, I have taken there, I have taken minus out, so that Cl alpha of wing times x bar AC of wing is here, and then I have taken this minus out, so it becomes plus eta St upon S, Cl alpha of tail times 1 minus dou epsilon by dou alpha multiplied by x bar AC of tail. Am I correct? So can I write this expression, right? Say, can I write this expression as x bar NP multiplied by this particular factor? Okay. So from this expression, so this particular term is Cl alpha times xAC of wing, eta HT St upon S, Cl alpha of tail 1 minus dou epsilon dou alpha multiplied by xAC of tail. So this expression I can replace it by xNP times the denominator here, right. So what I have is Cm alpha of the aircraft is equals to, so Cl alpha of wing plus eta of horizontal tail St upon S times Cl alpha of horizontal tail, right, Cl alpha of tail times 1 minus dou epsilon by dou alpha. Is that what this denominator is, right? And you have the same terms here. You have the same terms here. Okay, I am taking that common. Multiplied by x bar Cg minus x bar Np. Okay. So otherwise, in other words, what I can say is, so do you remember this particular expression is nothing but total Cl alpha of the aircraft. So this is Cm alpha of the aircraft. You just go back to our previous expression and see what is the total lift curve slope of aircraft, wing and tail combination. This is the lift curve slope of the total aircraft, isn't it? This is nothing but Cl alpha of the total aircraft. This implies, so Cm alpha is equals to minus of Cl alpha of the entire aircraft here. Cl alpha is Cl alpha of this entire aircraft, right? This particular term multiplied by x bar Np minus x bar Cg. Okay. So now will you appreciate my initial statement? So if this Np, if your Cg crosses this Np, that means this becomes larger than this. So this particular term is negative. So the expression becomes positive. So Cm alpha becomes positive for. So your configuration, no, the Cg of the configuration in order to have static stability, longitudinal static stability, your CG should be ahead of this neutral point. Okay. So this is the thing. So this particular thing, x bar NP minus x bar CG is equals to minus of Cm alpha upon Cl alpha of the entire contour. So this particular, the distance between this neutral point and center of gravity is called static margin, right? Static margin, Sm is static margin. So positive static margin means what? Neutral point is behind the CG, or CG is ahead of the neutral point of wing and tail combination, right? So static margin is equals to x bar NP minus x bar CG. Okay. So positive static margin is the neutral, CG is behind the neutral point. This quantity is less than this neutral point, x bar NP, right? Generally it is given in percentage, 10%, 5%, 15% static margin. That will solve. While solving examples, you will be more comfortable with the terms, right? And then, so this is equal to minus Cm alpha upon Cl alpha. For a statically stable aircraft, Cm alpha is negative, right? Negative of negative is positive. So you will have positive static margin, which means the CG should be ahead of the neutral point. So neutral point is nothing but the aerodynamic, similar to that of aerodynamic center of entire aircraft. Okay. So for a statically stable aircraft, Cm alpha is negative and negative of negative is positive. So Cl alpha we know for the entire aircraft is positive, of course. So if this is positive, which means xNP is this positive terms plus xCG, right? Which lies behind the neutral point, lies behind the CG location. So it's a limiting condition for stable flight and static stable flight and static unstable flight. Okay. And this is called static margin. So static margin is again is equals to minus of Cm alpha upon Cl alpha. Can you get something out of it? What exactly is this neutral point? Let's look about it in more detail. This is my perspective again, right? So it's a, you understood, right? It's like a limiting condition. Similar for a wing alone configuration, this neutral point is nothing but there is no tail here, right? This is nothing but XAC of wing. Am I correct? For a wing alone configuration, if you substitute CL alpha T is 0, XAC of T is 0, right? So this becomes 0 and CL alpha of T doesn't make sense. There is no CL alpha of T, right? These two terms disappear. This term and this term disappears. What I have is XNP is equals to XAC. For wing alone, x bar NP is equals to CL alpha wing times x bar AC of wing plus 0 upon CL alpha of wing plus 0, which is equals to x bar AC of wing. So for a wing alone configuration, neutral point is nothing but the aerodynamic center of wing. Okay. So in that case, you need to have, in order to have positive static margin, right, for a statically stable case, the CG should be ahead of this neutral point, which is nothing but the CG should be ahead of the aerodynamic center of the wing. Okay. That's the reason why even during our flat plate flight demonstration, we have shifted, by adding a small weight, we shifted our CG ahead of the neutral point there, even, which is aerodynamic center in that case, right? Okay. So now let's look at this neutral point in more detail. So we have calculated CG earlier, right? How have we calculated? So x bar CG in general is equals to, in general, for a, if you consider a mass, right, which is made out of M1, M2, right? So you have y-axis and x-axis. So this is at a distance M1 is at a distance of x1, M2 is at a distance of x2, right? And similarly, M1 is at a distance of y1 and M2 is at a distance of y2. So M3 is at a distance of y3, so on, right? So in this case, sigma I stands from 1 to n. So mi xi upon sigma mi, right? So which I can say, so xcg of a given body is like m1 upon m, where m is sigma mi, right, times x1 plus m2 upon m times x2 plus m3 upon m times x3 plus so on up to mn upon m times xn. So is it not a weighted average? So you have weights here. To each and every x1, x2, you have weights here. Weighted average. So CG is nothing but the weighted average of their locations. Weighted average of masses, isn't it? Here, weighted average by their masses. Right? Similar to that, can we look at this expression, x and p? So x and p is equals to CL alpha of wing upon the total CL alpha of the aircraft, which is like total mass of the aircraft, isn't it? So total mass of a body is like, so CL alpha of wing plus eta of horizontal tail st upon s times CL alpha of tail times 1 minus dou epsilon by dou alpha. Am I correct? So is it not the total CL alpha of the aircraft? So can I express this as the total CL alpha of the aircraft? Right? So this multiplied by x bar AC of wing, right, plus eta of tail, horizontal tail, st upon s times CL alpha of tail multiplied by 1 minus dou epsilon by dou alpha divided by, again the total CL of the aircraft, which is CL alpha of wing plus eta ht st upon s times CL alpha of tail multiplied by 1 minus dou epsilon by dou alpha. Right? So this entire thing multiplied by x AC of tail, x bar AC of tail. Am I correct or not? So neutral point is the weighted average of CL alpha, lift curve slope of wing and lift curve slope of tail. Do you accept this? Do you appreciate that? So let's understand it in a bit more detail, right? I think you are not happy with this. So let's understand it with a bit more detail, right? What exactly is this, are these terms, no? So they are disturbing a bit, isn't it? So let's assume a case where I have a wing here, right? There is one wing. Let's assume an identical wing which is at a far away, right? I have one wing, right? I have the same wing, similar wing, which is located at a distance in the downstream. I have two such wings, right? Do you follow that? So the area, which means the planform area is same, and the CL alpha of that wings are same, okay? And assume that there is very minimal downwash, there is zero downwash, okay? In that case, what happens? So I have a main wing with CL alpha, right? And then this particular downwash is 0, that means eta is equals to 1. So in that case, eta is equals to 1, and st upon s is 1 because I have two identical wings, one as wing and one as tail. So this becomes 1 in that case. Am I correct? And CL alpha of tail is nothing but CL alpha of wing. Both are same, and there is no downwash, that is 0. So this entire expression will turns out to be CL alpha of wing times 2 times the CL alpha of wing. Am I correct or not? Multiplied by x bar AC of wing. Okay. Similarly, plus, so this x neutral point in that particular case where you have two identical wings as wing and tail combination. Okay. So and then here eta of tail is 1, right? Because there is no downwash. So st upon s is again 1. So CL alpha of tail is nothing but CL alpha of wing. Am I correct? So downwash is 0, epsilon is 0. Divided by, again, CL alpha, 2 times of CL alpha of wing times x bar AC of tail. So this is nothing but, in this case, the neutral point is nothing but x bar AC of wing plus x bar AC of tail, that is nothing but wing 2 upon 2. It is just the midpoint of separation. It lies at the midpoint of the distances between x aerodynamic center of wing and x aerodynamic center of tail. How many of you appreciate this? Okay. So that is nothing but the neutral point. Right. So what are these terms here? So now you can understand, right? These are nothing but correction factors to the CL alpha. Am I correct or not? So when there is no downwash, that means this is gone and this is 1. And this is nothing but the correction factor for or normalizing factor for with respect to the wing. Right? When you have two similar wings, this becomes 1. This is just a normalizing factor. So this will be equal to the wing CL alpha itself. So this entire term is nothing but a correction factor to the CL alpha of that particular geometry. If it is a tail, if it is just an identical wing, that is nothing but one and the same. If the downwash is minimal, if the downwash is 0 and this efficiency is 1. Right? Do you appreciate that? So in that case, it is nothing but the midpoint of the distances separating these two wings. Right? So if you don't accept this result, we'll try to demonstrate it. Right? So in the next lecture, we'll have a demonstration of two identical wings, and I'll prove that the neutral point is the distance, like midway between their aerodynamic centers. Okay? Thank you.